Hello, my name is Gennady Staskevich, and I will be presenting a review of efficient forwarding information-based caching using minimal non-overlapping prefixes. Paper written by Professor Yao Qin Liu, Vince Lehman, and Lan Wang. So this is the rough outline of the paper. So moving on to the problem description or the motivation for this work. Internet is becoming an integral part of our society. The number of services that it offers is growing continuously, from cloud computing, banking, shopping, entertainment, social tools, legal services, transportation. It's just growing and growing. So we see every year there is a growth in this area. We see that initial address space that IPv4 was offered has finally been exhausted, and IPv6, which is the new address space scheme, is significantly larger, and it offers 2 to the 128th of possible addresses. It's extremely huge number as compared to the number of spaces available with IPv4. However, the adaptation rate for IPv6 has been somewhat slow, but at the same time we've seen a rapid rise of mobile devices, and now the new thing of Internet of Things, and we've seen many different types of applications that are previously we never would have thought would have been required the internet connection now, like our refrigerators, washing machines, coffee makers, vehicles, light bulbs, outlets. It's just, the list goes on and on of all the things that are being connected to the internet. And everybody is, or majority of these things are being controlled through trying to leverage the existing standards. As we can see that every device now needs its own IP address, and we can see that with the way things are going, we're going to run out of space and out of these addresses. And as people were predicting that the IPv4 address space was going to be exhausted way earlier on, even as early, I believe, as 2008, and every year or so, like a lot of people were predicting it's going to get exhausted quick, but it took a bit longer, and it actually sort of flattened out around year 2008, and some people suggest it may have been because of the economy, but it's really hard to tell. Next slide. So the challenge is, how do we come up with efficient routing? In the backbone of the internet, all these things rely on these or Internet of Things devices or interconnected devices require communications among themselves, and we tend to rely on many of these services now in such a way that they're pretty much part of our daily lives. Like, we rely on banking, electronic banking, and we expect these things to be available with like ATMs. So we need the backbone requires an efficient way of being able to handle all this traffic, and the speed of traffic is increasing, the network connectivity speed is going up, the bandwidth is increasing, and routers, they must be able to handle all these communications and packet routing at pretty much at line speed. And the challenge here is that these specialized routers are very expensive and difficult if not impossible to upgrade. So the companies that purchase these hardware devices have longer shelf life, around 7 years, that up to 7 years, and even some cases a bit longer, that they reuse these devices for routing, and by then they get outdated and can't handle the traffic efficiently. So the challenge here is to devise a specific a new protocol that is able to efficiently handle very large data sets, while at the same time minimize use of expensive hardware, specialized hardware, and being able to easily maintain and maintainable. Okay, next slide. So moving on, so the proposed solution has to be able to, as mentioned before, handle rapid growth of the routing table, because all those Internet of Things are requiring its own IP addresses, and being able to route all these things with all these devices efficiently. And another motivation behind this approach is that previous research showed that very few routes are responsible for majority of traffic. So we do not need to build these very expensive machines that use this specialized RAM, high-speed RAM, that is extremely expensive and very difficult to upgrade. So we can devise the basic idea here is that if we can use, since a lot of the routes generate majority of traffic, popular routes, so we can keep maybe just the popular routes in very fast memory, and everything else we can fetch on as needed basis, the less popular routes. So this approach, as we can see, has a very simple design. It has, as you can see, this image diagram of this architecture. We have a control plane and a data plane. And the control plane, we have a routing information base, RIB, right here. And this is where we get our routing updates. And the data plane right here in the lower section, this is where actually we're receiving actual traffic input, such as packets being routed, and the whole point of this FIB cache, forward information base cache, is to correctly, once the traffic packet arrives, we want to correctly output it to the correct line card, to the card output, so it goes to the correct router downstream. And this is a very simple design, conceptually simple design, that has very fast, a small quantity of very fast RAM that is able to store up to 20,000 most popular routes. And it has a slow RAM, local RAM, which is much slower. And this particular RAM, called forward information base memory, basically has a copy of the entire routing information base, entire routing table in memory. And when the new traffic comes in, what it does is it checks if this particular destination address is inside the cache. If it is, it just gets routed, passed through, and like nothing happens. It works. But if the cache, if the destination address is unknown, then what happens is this scheme will now do a local lookup, which is still much faster than what traditionally would have to go to the control plane, retrieve from the routing information base, and then push it down back. So this is a very efficient scheme, and we'll see it later on with a bunch of actual results that prove this point. So another thing to point out is that memory is based on Patricia trees or radix tree, which we'll cover in the slides in more detail. Routing information base that in the control plane is used to provide the initial population of the routing table. And as we can see, later on in the results, we'll see that we can run initial cache being completely blank, and how well this system handles or builds up its new routing table in fast cache, or if it's already initialized, how well it performs as well. So, next slide. So a little quick background on Patricia trees. This is typically used by like when parsing regular expression, which is very often used in like compiler design, and it's a tree structure. And what it does is this particular architecture or data structure allows one to easily or very rapidly compute if there is a match. For example, like the word romaine, we start at the root, romaine, and we'll go from the top to the left, almost leftmost node, and we'll spell this word romaine. And we can see that going certain path creates a particular tree. And if you start on a path and later on you get a new node that's not on a tree, that means you don't have that entry, don't have that match. So it's very efficient matching scheme. And this particular scheme is used for both very fast cache that's inside this architecture and the slower FIB memory. And let's see. Okay, so each node inside this cache has 3 fields. It has a prefix, as we can see in each one of these diagrams, like A :10, and then 2. So that's the prefix where for the network address, and then it has the next number after a comma is the next hop, which port it is supposed to go. And then the last character is a type of node, and various node types are used to compute the updates of the Patricia trees during announcements and withdrawals of new routes. Okay, next. So one of the issues that's identified in this paper, if one is not careful how they're designing their cache lookup scheme, then it is possible when we can for this problem called cache hiding to occur. This particular problem occurs when a cache when a new route comes in and we're trying to find so say this particular route has a prefix of length 5, and we match on a prefix of smaller length, less specific, more general or less specific in cache. But each one of those hits, like as an example in the previous page, for example, if we match on this B 1001 route prefix rather than on E if our initial lookup, then essentially this the shorter or the more general prefix will basically hide the more specific one, and this becomes a problem when the next hop differs in those two cases. So this packet will get routed to a wrong destination, and that's a problem. And this particular scheme actually does a pretty clever solution to this problem. So the basic idea is to, instead of generating smallest possible prefix length, what it does here is that we generate the smallest minimum possible length while still maintaining enough prefix length to be able to distinguish between routes. So if there is a shorter path description, like if the length is essentially not the leaf node in the tree, then what we have to do is we generate a new node that's called let's see, 1 second, a glue node, and we'll create new leaf nodes that will essentially become the most specific yet the minimum length, so you can still distinguish if it is indeed the correct routing path. So this is a workflow for cache miss. Essentially, in the first diagram where we had updates, and what happens, so the way we start is once this initialized, we're listening for packets, and this was in the first diagram we saw where the traffic comes to the left and it gets routed by this forwarding information based mechanism to the correct line card. So it listens here for the traffic, and once it sees a packet, it checks its fast cache. Is the cache already in memory? If it is, then it forwards the packet to the correct destination and goes back to the listening. Second case, if the cache is not in the prefix, then what it does is it queries a slower FIB, or a forward information base memory, and if there is no prefix, then it just discards that packet and goes back to listening. However, if there is a prefix, then this is the scenario where cache hiding can occur, potential, but not in this setup. But so this is how this avoids. So the simple case, if it finds a leaf node with the correct prefix, then it just updates the slow forward information base, and then it checks if the fast memory, the fast cache is not full, then it just does the update. If it is, then it does a cache replacement, essentially throwing out the least recently used entry, and then basically forwards the packet to correct destination and goes back to listening. And the last case is the more complicated one. So if it finds there is no prefix, and then it checks the forward information base, and it does find a prefix as an internal node in a tree. So this is where it will regenerate new prefixes, generating the new glue node, and push the new more specific node to the side. So now you can actually locate it, and it goes through the same path again, continues. Okay, so the cache update is a bit more complicated. From one essence is that it's using those node types to complete this task, and this is when new path arrivals come into the routing information base through the control plane. And basically we're looking here if there is a new route that's being announced, it goes to add new route, new prefix to the forwarding information base, and then we check, is the new leaf node, is this a new leaf node? If it's not, then we update the subtree for cache only, and nodes with hop, and then we synchronize with cache. And if the new leaf it's a leaf node, then we check the parent type, what kind of node is its parent, if it's FIB only or if it's cache only, and we do whatever it says in one of these boxes. And similarly, so this architecture basically describes the routing scheme, or not the routing scheme, the actual update with new routes, or removal of a route. And we'll hear there's more towards the end about the impact on the performance that this thing has. Okay. So the evaluation was implemented using the mininet. It was created with on a virtual network with 2 hosts and an open flow switch. And according to the references to the authors and the references in the paper that least recently used algorithm actually performed almost as well as the ideal algorithm. So a little background on the ideal algorithm was it's physically impossible to do it at runtime because this was done on already captured data set. So rerunning a data set, and we can actually estimate what is the optimal policy or when to remove certain or replace routes from memory from the fast cache, and which ones to add when. So this was least recently used algorithm was able to perform pretty much on par with the ideal algorithm, which was simulated. However, the current OpenFlow specification has limitations to it and made it impractical to implement either LRU or LFU, or least frequently used cache replacement scheme. The problem was that trying to do those things will require to get to query pretty much the entire data set of updates, and this is and you have to do this pretty much for every single one, and it becomes extremely computationally expensive, where it becomes where the scheme breaks and it's no longer feasible to actually so essentially this is too computationally expensive to execute. So this custom algorithm was designed and it was based on the experimental data in attempts to minimize the cache size and the number of times the prefix has been removed from the cache. And as we've seen that the evaluation of efficient FIB caching algorithm was carried out without having to modify existing hardware or software because of the using Mininet and virtual networks and two hosts and OpenFlow switch. And we'll see more details on that. So the OpenFlow was running on OpenVSwitch software. It ran on a virtual network with a VM that had 2 gigs of RAM, and it had 100% CPU execution cap. The host machine was 2.7 gigahertz Xeon E5 26 model 2680. Another machine was used for the OpenFlow controller, and it was programmed with POX. This was Pentium 4 that had 4 gigs of RAM. I don't recall seeing the gigahertz on that one. The controller and switch, they were communicating over TCP session established by POX. So this particular architecture utilized 2 different types of traffic data sets for evaluation. The first data set was from original ISP. It had 4.1 billion packets. It was over that were collected over 24-hour period. Okay. And the second data set was from backbone router. It had 2.5 billion packets that were captured over a period of 1 hour, and it was basically this data set contained tables and updates for 30 different routers, and this the distributions were amongst these different routers were very similar. So for the actual benchmarks, the authors used a single router just to show their point, as it was not necessary to utilize the other ones because it wouldn't make any difference. Okay, so one of the key ideas behind, or the motivations behind this efficient forwarding the scheme is that the traffic distribution basically shows that most of the traffic is generated by very few traffic routes. So there is extreme high popularity. As we can see, the graph shows log scale in the x-axis for a number of prefixes. And on top we see the cumulative percentage of hits, or how often there is a cache hit in efficient fast memory. And we can see that with only 10 first packets, we get pretty much almost 42% of the we can build up our routing table that will have 42.79% of routes. And if we capture 100 packets, then we're going to rapidly jump from 42 to 79%. And to get higher, as you can see, for our 1,000, our accuracy goes up to 93, and 10,000 it goes to 99.51, and 20,000 it goes up to 99.87. And so most of the entities in a global routing table are not even in use during this period. So one of the key observations here is that the data for both sets, so there is two lines here. One is for the regional ISP trace, and the other one is for the backbone. And for the backbone, it's only for the single one, not for the aggregate. And we can see that they're very similar, and they're almost so both show that popularity plays a key role in this chart, and that we can actually utilize a small, fast, expensive, and highly efficient RAM for storing popular routes and still get blazing fast performance with minimal hit to the least or less important routes, or less frequent routes. So here we're looking at this regional router benchmark, and trying to compare the cache size, how big the cache size, to the number of actual hits. So if our cache size, say 1,000, can store 1,000 prefixes, or can store 2,000, and we can see significant jumps in the initial in performance. We go all the way from like 96 to nearly 100 if our cache size goes to 20,000. And but the thing is, we're already starting at very high hit ratio at 96%, and we can see that the performance, like the very popular routes, is that only few popular routes control all this traffic, and shows that efficient further reinforces the idea that the small cache size will be efficient if we for this system. But the negative, or the downside to this, is that to make a small increase in performance, we have to significantly increase the number of packets. Another thing, Leslie, almost forgot. The dip in this particular charts is showing at particular time. This was early in the morning, and there was actually like a dip in number of packets received. So I guess early in the morning, this was like a morning around 7:30 or even earlier, somewhere around that time. I guess not too many people using the internet. Okay, so here's the again similar idea, but this time the benchmark is for the backbone router, and we're comparing. Here is the efficiency, and we can clearly see that the performance, the hit rate is even higher than for the regional one, and the ideal deployment for this FIB scheme, efficient caching scheme, is to be deployed for the backbones. And we can see that even with 1,000 size of 1,000 prefixes, cache can be very effective at almost 99% performance. But if you just double it, it goes into almost close to 199.6 and higher. So this further reinforces the idea that this scheme is highly applicable, or at least will be highly valuable for the backbone router. Okay. So here, this chart basically compares various approaches that are trying to implement this efficient routing, and we can see that the approach that was presented in this paper outperforms all the other approaches pretty significantly. And we'll see a more concrete example further in the next few charts, how actually the actual calculation cost in time cost is that this is pretty much efficient and given the highest performance. So this is definitely one of the best performing schemes for the efficient routing. And here we're comparing, what if you were to compare this or benchmark this routing scheme if you did not initialize the cache, the very fast cache, because some the other ones, the cache was initialized, I believe, with close to 10,000 packets. Okay, it doesn't matter. So the other ones were number of packets 100. So if we initialize packets or initialize our fast cache with 100 packets, then we can see our initial performance pretty much starts out at 85. And since this is a logarithmic scale, we can actually see that we're pretty much approaching 85 with about 20 to 30, I'd say 20 packets actually will likely reach the 85 packet ratio, or 85, 85 I guess. After 100 packets, after we get 100 packets, we can see that the delta between these two lines is less than 5% ratio, and almost shrinks to zero at 1,000 after 1,000 packets. So this scheme shows that this routing scheme is extremely efficient at building up popular routes, and it will be able to handle a lot of traffic very efficiently. So here, this chart is actually kind of an interesting chart that kind of measures the performance of this scheme. So the top curve, we see the total number of RIB updates that we receive. The middle curve is the total number of updates pushed to the cache. And the bottom curve is the number of prefix deletions. And in the paper there is a good explanation for showing that this is extremely fast, and the number of deletions pretty much have, or the updates have almost no influence on the cache hit ratio. That's how efficient this scheme is, or this routing scheme. Also, the cost for processing various so comparison between various approaches such as atomic block, uniclass, and with this algorithm presented in this paper, and we can see that it's linear and it's almost on par with the most with the lowest cost. So it's extremely efficient, and my belief, the efficiency for this is due to the Patricia trees, how effective the caching scheme is at building the minimal length required to get the unique prefixes. And these updated trees are extremely effective, and we're reaching very high performance, approaching almost 90, 99, almost 100%, I would say. So this particular chart compares to the least recently used algorithm through simulation, and it shows that it's almost on par with it. So it's extremely efficient, and this is probably the best you're going to get in the real world. And this further reinforces the idea that this approach is feasible and viable for real world caching, forward information based caching implementation. And I think it will do really well implemented on the real hardware. And so some of the takeaways, for me, really liked the paper. The presented approach was simple, effective, cost-efficient design. It has potential to significantly reduce equipment costs for the network providers. And the authors did a really great job at conveying their ideas by showing their pseudocode. Great for anybody who's interested in implementing this architecture. And they did also, likewise, they also provided diagrams great for anybody who would like to get a great, simple idea of what is happening. So I really enjoyed this paper. And if you have any questions, please submit to my email. And my email address is staskivg@clarkson.edu. Thank you.